Doug, do you want to go to full screen mode?
Is everyone seeing that okay? Great. This video. I see both our presenters are here, so we'll start momentarily.
Do you want to start, Doug?
Yes. Hello and welcome to the IEEE Photonics Journal Club. Today's session is supported by Photonics Technology Letters, and this is the June 2025 session. Thank you everyone for joining. I'm Douglas Hargis, Senior Publications Administrator with the Photonics Office. As I said, this is supported by IEEE Photonics Technology Letters, or PTL, and the IEEE Photonics Publications Council. A little bit about our society. The IEEE Photonics Society, or IPS, forms the hub of a vibrant technical community of more than 100,000 professionals dedicated to transforming breakthroughs in quantum physics and devices, systems, and products to revolutionize our daily lives. The cornerstone of IEEE Photonics Society is the partnership between staff and volunteers with a common goal of promoting the exchange of technical information, where scientific and engineering advances in photonics are shared and nurtured. This is the IEEE Photonics Society portfolio of publications. Today, we'll be focused on Photonics Technology Letters. And as you can see, we have a variety of different publications across the disciplines of photonics. A little bit about the Journals Club. It's a regular gathering of scientists to discuss a journal paper found in a research journal. The IEEE Photonics Journals Club program was created to help connect students and early career professionals with the researchers and authors of prominently published research papers. How it works is the participants read chosen scientific papers picked by the journal's EIC, and they attend a session with the published authors. The authors present their published research where participants can ask direct questions about the work. The end goal or end results are you can connect directly with authors in the field and gain advanced technological knowledge, better understand the benefits of scientific publishing and peer review. And at the end, we allow for a Q&A session where you can inquire about the aspects of the design and methods behind the research. Today's presenters and our moderator. Our first presenter is Zhou, Polytechnico di Milano. Our second presenter, Younghai Liu, of Peng Cheng Laboratory, Shenzhen, China. And our moderator is Professor Boon S.Ui of KAUST, Saudi Arabia, the editor-in-chief of Photonics Technology Letters. I'd like to thank them for all joining us today. Yes, so we'll kick off here. Allow me to introduce our moderator, Boon. Boon S.Ui is a professor in electrical and computer engineering at King Abdullah University of Science and Technology, KAUST, Saudi Arabia. He is editor-in-chief of the IEEE Photonics Technology Letters and an editorial board member of the proceedings of the IEEE. And at this point, I will turn this over to Boon to introduce our first author.
Boon, you're muted. You're muted.
Oh, I'm sorry.
We hear you now.
Thank you. Thank you, Doc. Sorry for
no
that.
worries.
All right, so let me introduce the first speaker, Xiaohui Zhao. Xiaohui Zhao is currently doing a PhD in the Department of Electronics, Information and Bioengineering at Politecnico di Milano, Italy. And I guess he's now doing an internship in France. His research primarily focuses on multi-band inductive optics amplifier, particularly on semiconductor optical amplifier for high throughput optical fiber transmission system. Today, he's going to share his paper on multiple tens of terabit per second real-time data center interconnects transmissions using a single SOA, a single semiconductor optical amplifier. Yep, Xiaohui, go. The floor is yours.
Okay, first I will share my screen.
Sounds good.
Can you see it now?
Yes, very well.
Yes.
Okay. Then I will start. Thanks a lot for your introduction. My name is Xiaohui Zhao. The topic of my presentation today is 67.2 terabit per second real-time DCI transmission demonstration using single seamless SOA. First of all, I would like to take the opportunity to thank all the co-authors. My presentation is mainly divided into 4 parts. First, I would like to move on to the first one, introduction and motivation. Nowadays, the traffic demands related to data centers have exponentially increased due to the application of machine learning technologies, the increasing complexity of models, and the growing training processes. Shorter reach data center interconnections and the data center networks typically span a shorter distance of 80 to 120 kilometers, where the cost efficiency becomes a key priority. Most existing DCI architectures are currently limited to operating within the C-band, mainly due to the lower fiber attenuation and economical amplifiers. Expanding the transmission bandwidth to other bands, increasing overall capacity. However, it requires to develop new cost-effective application schemes. Most amplification technologies expanding bandwidth are scaling up the number of amplifiers, which greatly increase costs. A cost-effective solution is to use one single amplifier to amplify multi-bands. Semiconductor optical amplifier offers several advantages, which makes it very potential approaches. And in this experimental work, we use a single seamless ultra-wideband SOA as booster and pre-amplifier to amplify both C and L bands. We investigate 3 different input power spectra and 3 distinct span losses. We also quantify the gain and noise figure of ultra-wideband SOA. Finally, we perform the optimal total real-time throughput across all channels in C and L bands. In the second part, I will present the experimental setup. There are mainly 3 parts: transmitter, transmission line, and receiver. At the transmitter side, two amplified spontaneous emission noise source are used to emulate Gaussian noise signals, providing 22.5 dBm and 17 dBm total output power for C-band and L-band individually. And then wavelength selective switches shape the AAC noise source to emulate WDM channels, covering around 6 terahertz bandwidth in each band. In C-band, there are 60 channels, and in L-band, there are 78 channels. The channel of interest signals are multiplexed with AC emulated channels using WSS. C-band transmitter supports only one. C-band transmitter supports two working mode with 91 gigabaud symbol rate, while L-band transmitter only supports one working mode with 68 gigabaud symbol rate. It should be noted that loading AEC emulated channels is commonly used to obtain a lower bound on system capacity, as it enhances both fiber nonlinearity as well as SOA nonlinearities. Then, the signal is amplified by a single ultra-wideband SOA booster, which incorporates a polarization diversity-based structure, as shown here. The transmission line consists of a single 100 km standard single-mode fiber. Variable optical attenuator is used to tune the total span loss. A second dedicated ultra-wideband SOA is used as a pre-amplifier, which has the same design and characterization as the first one. At the receiver side, after demultiplexing, the signals are separately amplified by the second stage amplifiers. The channel of interest for each band is then filtered using respective WSS and then sent to the real-time coherent receiver. It allows us to measure the bit error rate results, and then we convert it to signal-to-noise ratio for better comparability of performance across different modulation formats. The optical spectral analyzer is used to measure the optical signal-to-noise ratio and the total power at different measurement points from P1 to P5. In the third part, I will focus on the results analysis. To investigate the most effective input power spectrum to achieve the highest real-time total throughput, we implement three distinct input power spectra of SOA booster, denoted as a pre-emphasis. The total output power of the SOA booster is fixed at 22.5 dBm for different pre-emphases. The span loss is also fixed at 25 dB. First, we tested the first pre-emphasis, achieving flat input power spectrum to the SOA booster at P1. The results shows in the figure on the left. Here, plot A shows the input channel power profile at P1 is quite flat as expected. Plot the measured OSNR at 0.5, and plot C shows the SNR measured at receiver side. The x-axis represents different wavelengths. Here we could observe a significant imbalance in both OSNR and SNR between the C-band and L-band. The C-band SNR values of the forward error correction limit for 600 gigabit per second is about 13.5 dB. Approximately 3/7 of the channels at longer wavelengths within the C-band support 600 gigabit per second, while the remaining 4/7 within C-band only support 400 gigabit per second. It gives the estimated real-time total throughput equal to 59.2 terabit per second. And then we tested the second pre-emphasis, achieving flat output power spectrum of the SOA booster at P2. In order to achieve so, we need to change the input channel power profile at P1 to mitigate the gain variation induced by the SOA booster. It's corresponding to the green marker in plot A. The same as before, plot B and C shows the measured OSNR and the SNR. We could observe the improved balance in OSNR and SNR between the C and L band. The worst SNR performance located at the shortest wavelength of the C-band. Comparing the previous one, it improves from 7 dB to 11.5 dB. Approximately 4/7 of the channels at longer wavelengths within the C-band support 600 gigabit per second. And then it gives the estimated real-time total throughput equal to 61.2 terabit per second. Finally, we tested the third pre-emphasis, achieving flat output power spectrum of span at P3. Also, in order to achieve this, we also need to change the input channel power profile at P1 to mitigate the gain variation induced by the SOA booster and to counteract the SRS power transfer corresponding to the red markers in plot A. Comparing the two others, we could observe it has larger variations. And then for the OSNR and SNR, we could observe that they are nearly the same for all channels. All channels in the C-band support the working mode of 600 gigabit per second. For L-band, a slightly degradation appears in both OSNR and SNR, but still remain well within the requirements for 400 gigabit per second. In order to perform the total real-time throughput, we swapped the channel of interest for all 138 channels across C and L band, and it gives the results of 67.2 terabit per second, which is the optimum results. For this optimum pre-emphasis, we characterized the gain variation and the noise figure for the SOA booster, the blue marker, and the SOA preamplifier, the red marker. First, we compare the two gain curve, which corresponds to the left axis. We could observe the SOA booster gain shape has lower gain at shorter wavelengths, and it's mainly due to the SOA saturation. The difference gain profile between SOA booster and SOA preamplifier is mainly due to the different input powers since they have the same design. For SOA preamplifier, it exhibits a relatively flat gain and low noise figure across the C and L bands. Since we are using single ultra-wideband SOA booster to seamlessly amplify signals across both C and L bands, it's crucial to maintain a sufficiently high output power for the SOA booster. We'll introduce more nonlinearities from the SOA booster and the fiber. The total output power of SOA booster remains constant at 22.5 dBm for 3 cases, but the power spectrum varies. We characterize the nonlinear noise-to-signal ratio for 3 different pre-emphases. 3 different markers represents 3 different pre-emphases. We could observe the NSR, NL remains relatively similar. However, it becomes larger at shorter wavelengths within the C-band. At this shorter wavelengths, it's slightly larger for the optimum pre-emphasis, which corresponds to the red marker. It's mainly due to the higher input channel power. To investigate the impact of varying span losses on transmission performance, we also adjusted the attenuation of the VOA to test 2 more span losses, which corresponding to 28 dB and 32 dB. The results shows here different markers corresponds to different span losses, and the same as before. Plot A shows the measured OSNR at P5, and plot B shows the measured SNR. Both are all 3 cases are implementing the optimum pre-emphasis. Across different channels, a nearly constant degradation can be observed in both OSNR and SNR. With a span loss of 28, the green markers, approximately 3/7 C-band channels can only support 400 gigabit per second. When the span loss increased to 32 dB, all C-band can only support 400 gigabit per second. Because of this degradation, when the span loss increasing, the estimated real-time total throughput decrease when the span loss increase, but still remain efficient for larger span loss. With 32 dB span loss, the total real-time throughput is equal to 55.2 terabit per second. Finally, I would like to conclude my presentation. So we have experimentally demonstrated an amplification scheme for the DCI transmission system using a single seamless ultra-wideband SOA as both the booster and first stage preamplifier across C and L bands. We have evaluated the transmission performance variations, including the system nonlinear impairments, by examining 3 different input power spectra and 3 distinct span losses. The results highlight the importance of optimizing the input power spectrum to effectively compensate for wavelength-dependent fiber loss, SRS, SOA gain profile, and system nonlinearities. By testing different span loss, the results also shows that the amplification scheme remains effective in high transmission losses. Finally, we achieve a total real-time throughput of 67.2 terabit per second over a transmission span of 100 km SMF with a total span loss of 25 dB. That's all. Thank you very much for your attention.
Thank you very much, Xiaohui. We'd like to leave all the question, the Q&A until after the second speaker. Since this is a journal club and I just checked the participant, we have very small participant. I really hope that we'll be able to make it more interactive. And other than the technical question, the audience are welcome to ask question related to essentially anything related to publications, scientific publication related to the technology trends along this line of research, particularly on optical communication, and also maybe talk about the career development as well. So audience are encouraged to tap your question in the chat so that we can then read out the question. Let us move to the second speaker. Let me introduce the second speaker. The second speaker is Yunhong Liu. Yunhong Liu is now pursuing her PhD currently at Pengcheng laboratory. I think Pengcheng is still relatively new, but is extremely well equipped, and a lot of very top communications scientists working in this particular institution in Shenzhen, in Shenzhen, China. Her work is primarily focused on optical fiber communication system, and where she investigates advanced technology to enhance data transmissions efficiency, signal integrity, and network performance. Yeah, Yunhong, please, your floor is yours. Share your slide, please.
Yeah. Okay. Good evening.
All right, good, thanks.
Yeah. Good evening, everyone. My name is Yunhong Liu from Pengcheng Laboratory, Shenzhen in China. The presentation is entitled as Optical Wireless Communication Enabled by Wideband, ASE Source, and Grating. Here is the outline. According to the ITU's Global Mobile Data Traffic Forecast, wireless data traffic grows by over 15% annually, leading to explosive data value growth. The table on the right shows nearly all data service traffic will at least double by 2030. The rapidly demand for wireless transmission capacity drives continuous advancements in OWC technology. Depending on the application scenarios, OWC can be generally typed as short range, medium range, long range, and ultra long range. In this talk, we mainly focus on short-range applications for indoor optical wireless connections. The indoor optical wireless communication includes visible night communication, YLC, and beam-steered infrared communication, BSILC, and Wi-Fi. BSILC operates in the 1416 to 1625 nanometer range. It connects terminals by directing infrared beams, eliminating the need for macro protocol with a transmission distance of about 10 meters. It features no power consumption and relies on FTTH infrastructure. VLC uses the 400 to 700 nanometer range. Over short distances, a few meters, it can achieve speeds of up to 9.5 Gbps per second. However, it requires an efficient macro protocol and has higher power consumption. Wi-Fi operates in these bands with a shared capacity of up to 7 Gbps per second. It provides medium range coverage, but base stations consume over 100 mW of power and depend on wired infrastructure. Thanks to mature standards, Wi-Fi dominates over 15% of global internet traffic. Let's make a further comparison YLC and BSILC. YLC utilizes existing LED lighting infrastructure for data transmission. The singular strength weakens with distance, and the technology cannot penetrate walls. The singular strength BSILC operates independently of lighting systems. It connects to user terminals, directing infrared beams, and allocates the dedicated beams to each terminal. Its direction naturally results in a higher received power compared to YLC, leading to a higher singular to noise ratio, faster data rates, extended coverage, and improved energy efficiency. Moreover, infrared light is unsafe, allowing for higher transmit power within safe limits. The beam steering has several approaches, which may be classified in using active steering devices and using passive one. In active beam steering devices, MIMOs, special light modulators, SLMs, the state of the devices is changed by means of separate control channel, implies a change in the beam's direction. Both solutions need a steering element per beam with its separate control signal. Passive beam steering devices, that means can be done by passive devices. Such passive function may be implemented by diffractive devices, through which the beam steering is controlled by changing the wavelengths of optical data signal fed to the devices. It just requires that multiple wavelengths are fed to the devices. That also means that multiple lasers are needed, where each wavelength independently determines the direction of its beam. Table 1 summarizes typical BSILC demonstrations using 5 beam steering techniques and their key property comparisons. MIMOs or SLMs require separate control elements for each beam, limiting scalability in multi-beam scenarios. The diffractive 2D grating enables continuous steering in one direction via wavelength tuning. The AWG plus 2D fiber array technology achieves by direction stepwise beam steering via remote wavelength tuning. With beam count limited by AWG output ports, steering speed ranges from nanosecond nanometer delta to 2 microseconds. MMF banding of low cost and fiber compatibility by controlling model coupling or offset launching. Then I will introduce the method and the experiment. To serve multiple users or terminals, MIMOS and SLM-based OW systems are hard to realize, while multiple tunable lasers are required for grating and AWGR. In this paper, we propose a low-cost scheme to realize wavelength-routed beam steering systems by using a wideband ASE as a net source and grating to disperse the wideband signal instead of using multiple independent tunable laser sources. In our experiment, a C-band EDFA was used to emit broadband light. The light is then passed through a self-developed wavelength selective based on ELCOS devices. 3-band signals were selected from the wideband light. The selected signals were optically amplified by another EDFA and modulated by an EAM, while the 1.25 G-band OOK signal was produced using AWG. The used fiber kilometer to transmit light from fiber into the diffraction grating in free space. After 2.1 meters free space link, a matched fiber kilometer was used to couple the free space light into the fiber. The received optical beam was optically amplified by the third EDFA, converted into electrical signal by a photodiode, and finally acquired by oscilloscope. Then I will introduce the results and discussion. To elevate the communication performance of the wireless transmission system, we investigate the BER and the different filtering bandwidths as ROP. The measured results show the BER performance at the 1545 nanometer exhibits the best trend. Moreover, as increasing the filtering bandwidth, the BER performance is enhanced significantly. At the 6.7% FEC limit, the achieved receiver sensitivity are -20 dBm. We further investigate the link power loss as a function of different wavelengths at different transmission ratios. The link power loss here includes the insertion loss, coupling loss, and propagation loss. The measured result indicates that the transmission loss is not proportional to the transmission distances. This mainly attributes to the use of matched fiber kilometers with long working distance in the demonstration. Since the kilometered beam has negligible performance variation within a typical indoor scenario, the result showing the about 2 dB maximum power fluctuation after 2.1 meters free space transmission. We have propose a low-cost wavelength-directed beam steering OWC system. The concept of experiment with 1.25 gigabits per second data rate per beam has been successfully achieved by a C-band EDFA at single occurring wideband net source. That was thank you, everyone.
Thank you very much, Yun Hong.
Oh.
Since we only have about 12 of us, so instead of typing your question in the chat box, I suggest we just raise our hand if you have any question, then we can and unmute yourself before asking the question. Is there anyone from the audience who would like to raise any question for our two speakers? If no, then maybe I can kick start by oh yes, Robin, do you want to go ahead? Robin, if you can unmute yourself and then go ahead, please.
Yeah, I was wondering if you're concerned about maintaining a line of sight so that communications transmissions aren't interrupted, or and how you might get around that.
Yun Hong?
Like in a busy office environment with people moving around and so forth.
You might want to unmute yourself, Yun Hong. You need to unmute yourself, Yun Hong. We cannot hear you. You need to unmute yourself. Yun Hong, we cannot hear you. Unmute, please.
We can see you're trying to present, but we can't.
Oh,
Oh,
okay,
now
okay.
we can hear you.
Share the slide.
No, the question is, how do you maintain the line of sight, say point-to-point connections in your system?
Can you?
Right.
Yeah.
The question from Robin was how do you maintain the line of sight? Because if you want to have the optical wireless comm, you have to have your transmitter aligned to your receiver. So how do you establish this line of sight? By adopting your technique.
We use the collimator to control the 2 collimator next the position to control the night and the steering. The collimator work distance is 100 meters. So in this experiment, the collimator is under 10 meters. So we can expand the distance. It's okay.
So
Yeah.
does it mean the line of sight will still have to be maintained, or it means that the grating after dispersing all those different wavelengths, you will still have to put your receiver at a fixed location? Is that the case? Is that the case in your experiment?
Yeah. Yeah, we can control the collimator placing to coverage the coverage information. Okay.
Is that all right, Robin?
Yeah, but I'm thinking it more like in a practical environment, say an office with people moving around near desks and devices. There's likely to be movement that's going to break the connection. So I'm kind of imagining a solution where the optical communications maybe stays above where people and most movement would be, and then maybe a fiber or some other sort of wired connection from that receiver down to a device, maybe to avoid any kind of interruptions, just in a regular day-to-day kind of in movement. But yes, thank you.
Thank you, Robin. Any other question from the audience? But if no, then I maybe.
Actually, I've got one.
Okay, please, Pat.
Yeah, I know. I see that the goal is a low cost system. For the experiment, you're using 2 EDFAs at the transmitter, and it looks like you might be using 1 EDFA per wavelength on the receive side. Can you comment on, if you were to implement this, how would the hardware look in a real implementation? Would you be using EDFAs in these numbers?
Oh, okay. That depends on our experimental measure results. We firstly the one EDFA function as a ASE source. It outputs the wideband signal, and then it passes through LCOS function as a field filtering. So so the signal pass through LCOS, the optical power is decreased. So we then use the EDFA to amplify the signal. As for the third EDFA, because the light is passed through the free space and the optical power is so we can decrease. So we need the third EDFA to amplify in order to reserved by PD or oscilloscope. Yeah. Okay.
Pat.
Yeah, okay. So I guess yeah, I understand where you're using those amplifiers, but I guess the question is, the expectation is that maybe isn't so low cost, but maybe you could do something. Maybe you could use devices that are more like the broadband SOA that was used in the first talk to reduce the cost of these things. And then I guess I wonder what maybe you could look into the limitations of, I guess you would have to compare it to a system that uses more conventional laser sources like a comb source and compare this. I'd be curious to see how much amplification you would use if you had more power per per wavelength. For example, what is the after the LCOS, what is the power in each of those modes that you have there?
Yun Hong.
Okay.
Right. The first question, the first comment is how practical it is, because you now have to use 3 stages of EDFA. So is there a more practical method to for the entire system? EDFA before the PD, for example, as a preamplifier, which can you consider say using SOA, like what Xiaohui was mentioning? How practical it is? Is it a practical system that you're proposing, or can it be further improved to make the entire system more practical and low cost?
We use the first EDFA function as ASE. It can save the motor lasers. Let's say the first setup, so we can iterate multiple lasers. The second setup can decrease the lasers, and it goes through two-naive filter. It can reach the it can be filtering matter wavelengths. So okay.
Right.
No, thank you. I'm good. I think, unfortunately, the language problem, I think it's hard for her. I mean, I don't know if you guys speak the same dialect. Would it be possible to translate? Or maybe we could just take it offline. I mean, I don't want to, I mean, it's hard to give a talk in, when it's not your native language. I feel bad even.
Right. Yeah.
I don't want to press it too much.
I understand that fully. Yeah. I'm not that fluent in Chinese, also I'm Malaysian. But I guess we can maybe discuss it through email, and Pat might want to discuss
maybe
with
it's
you.
better via email. Yeah. Yep.
Any question for the first speaker, Xiaohui?
Okay.
Thank you, Yunhong.
Okay.
If not, then maybe I can kickstart by asking Xiaohui. You mentioned a lot about the cost efficiency, but energy efficiency essentially is quite critical, a critical considerations in data center interconnect as well. Do you have any comment on the energy efficiency of your proposed system?
Yes, thanks a lot for the question. So, in our work, actually, we were, I mean, the main idea is proposing using one amplifier to amplify both bands. Of course, it will reduce the costs. Actually, due to the same reason, actually, in my opinion, it also will reduce the energy efficiency because in the transmission line, the amplifier, the energy provided for the amplifier definitely will become one of the most important part to maintain the whole transmission line to make it operable. So using one amplifier instead of two amplifier to amplify the two bands definitely will reduce the energy efficiency, of course. And since we were using the SOA, the amplifier it can be operate. I mean, the amplifier it works. Also need some frame to support it to works. So by reducing this amplifier, it also reduce the frame support the amplifier to operate. It's another kind of way to reduce the energy used in one transmission line. So actually, it's in my opinion, actually, it's a right direction to reduce the to make the transmission line more efficient for the energy. So in my opinion, using the same way is not only to make the transmission line more cost efficient, but also the energy efficient.
Yeah, thank you, Xiaohui. Anyone, any other question? Right? If no, then maybe
Yeah,
I'll yeah.
I was going to say this is Pat again. That's a very nice device you're using there. I'm curious about the I guess when you're using it at the 22 dBm output power, I would expect it. When you're in saturation like that you would get less gain at the short wavelengths. I'm just curious to know, is the degradation in performance, is it just due to the decrease in gain, or I assume there's also a contribution from cross gain modulation? Is that true? Like, is there a penalty? Is part of that a penalty from cross gain? And if so, I'm curious to know how much cross gain, what the contribution of cross gain is at the short wavelengths.
Yeah, thank you for your question. It's actually it's a really good question. In our experiments here, actually, I was supposed you are talking about the SOA booster side, right?
Yes, exactly. High
So
power.
yes, the high power here, it's very crucial that since we were using one amplifier to amplify both band, and we want to make all the channels with a very good performance. So because the SRS actually is the beginning of the C band, it's the most difficult part to maintain. Here we were fortunately actually our device is quite good, even with very large SOE saturation, located at the shorter wavelengths in C band. Even with a large saturation, the gain decreased a lot, but then the nonlinearity introduced, it's still low. Actually, this device is designed to operate in this kind of condition. So, of course, as you said, here actually, especially at the shorter wavelengths in C band, it's suffering both, not only the gain degradation,
Right.
but also the nonlinearity, of course.
Yeah.
But since this device was designed to for this kind of application, even with this kind of nonlinearity, as I showed in the results, it's still capable to support high performance transmission. And
Very
here, the most difficult part is to maintain the total power here, actually. As I showed, the SOA gain at the shorter wavelengths in C band, the SOA booster is the gain is very low. So this is a crucial difficulty that we meet. We need to find, actually in the future work, we need to find a near better design or better condition to find a way to increase the SOA gain at this wavelengths to further increase, to further make the performance better.
Yep. Yeah, no.
Yeah.
It's a challenge. Very nice result, though.
Yeah. Thanks. Thank you very much.
Any other question for the two speakers? Maybe I have one for both of you. Since one of you is talking about the optical wireless communication, and the other one is in the data center interconnect. First to Xiaohui, do you see the possibility of using free space optic communications for the not too long connections, right? They're talking about, say, up to a few hundred kilometers or so. Do you foresee that this is possible by using free space optical communication?
Thanks for the question. And in my opinion, actually, I will consider actually it's two application cases. Actually, I will agree that I will say that the free space communication will definitely have its advantages and will, this application, of course, in the practical, I mean, in the practical applications, it definitely has it's still usable, and for my study, actually, it's for the moment it's still span I would say longer than the free space communication that's supported. As I mentioned that this study is mainly span of 80 to 120 kilometer. For this distance, free space, I would say to make it practical, usable, it's still challenging for the moment.
Thank you. Yun Hong, do you have any comment on whether OWC one day will be able to use for the data center interconnect application? You're muted. Yun Hong, you are muted.
OWC systems application is mainly in indoor and short range scenarios, like for example, we when we are at home can use OWC systems to transmit the data from the base station. Okay.
Yeah, thank you, Yun Hong. Yeah, in fact, SpaceX, I guess many of you are aware of, they announced the satellite to ground and being able to get multiple 10 to 100 gigabit per second. And yeah, that is simply based on the optical wireless, that is space optical communication. Yeah, that's why I was thinking about whether beam steering would be able to reach that far. And I understand the limitation of the beam steering is mainly on the in the indoor and couple of meters reach. Any other question from anyone? We still have about 2 minutes before the end. If no, maybe I'll suggest we close this session a minute earlier. Yeah, I would like to thank the two speakers again for giving a wonderful overview of your research and the presentation. Doug, back to you.
Yes, I'd just like to conclude this meeting. Thank you for all the attendees for showing up. We will have a recording of this on our website. Thank you to Boone for moderating. You did a great job, Boone. And thank you to our speakers, Xiao Wei and Young Hong, whom I'll be in touch with after this. So thank you, everyone. And please be on the lookout for our next Journal Club meeting.
Thank you all.
Have a great day, everyone.
Yeah, thank you.
Okay,
Thank you.
bye-bye.
Thank you.
Bye.
Thank you. Bye.
Bye.
Thanks.